Okay, today we're going to talk about section 6.2 of your book that goes over angular velocity and linear velocity. This is going to be a section that has a lot of real-world application problems, so expect this whole part to be pretty word problem heavy. If that's something you struggle with, just make sure you're keeping that in mind as we work through this, that may mean you need to come see me so that I can help you out to go over any of the questions you may have. So angular displacement is the first thing we're going to talk about in this. Your angular displacement is always your theta in a problem, and it's really just the same measurement as your central angle. What we're talking about is as you turn in a circle, how many degrees, or really we're going to talk about it in radians, are you rotating through? So it's your angular because it's the rotation that we're thinking about, which is really just an angle, and displacement, how much you changed. As we go through this, it is going to be crucial that we are talking about radians. If it's in any other unit of measure, it's not going to apply correctly as we move further. And so we're going to use these conversions down below as we talk through this, and that's what we're going to look at here first. What I'm going to do here today is talk about pretty much all of this the same way we do in chemistry, because there's a lot of dimensional analysis or unit conversion that can be done more simply as long as you think about it the same way chemistry thinks about stoichiometry. So if you're in that unit or class, or if you've had that class, this is going to be something that you've seen before, but I'm going to go over really how that process works. So if I want to convert revolutions, we already taught you technically a way to do this using cross-multiplying in your proportions in previous classes, but again, I'm going to show you a different way. When we do stoichiometry, you draw your line, and we're going to place what we're given over here in the 3 revolutions. And each section of this, you can have multiple, here we're just going to have one, is going to be my conversion factor to get from revolutions into what I want it to be. An angular displacement always needs to be in radians. What I think about when I do this is I need to cancel my unit of revolutions. So I'm going to put revolutions down below so that these units will cancel out, and my units will instead be in radians. So now what I have to think about is how I actually do that, because I can't just cancel it. It's not a one-to-one conversion, but I know that 1 revolution is the same as 2 pi radians. If I do this, when you're doing it, anything on top will multiply. You can technically multiply straight across either way, and then you will do the top divided by the bottom. So here I really just have 6 pi radians. Again, there are other ways to do that, but this will come in handy, especially as our problems become larger. So I'm going to try out this second one, 4.25 rotations. Oops, there we go. Again, I want to switch from rotations into radians. I need my rotations unit to cancel, so I need the rotations on bottom. But I know 1 rotation is 2 pi radians. Again, I'm going to multiply straight across, so this is 8.5 pi radians. Number 3, again, we already talked about specifically going from degrees to radians before, but I like to always show you how you can use stoich for this as well. So again, my 540 goes on top. I'm trying to cancel my degrees, so degrees would go on bottom. So this would be 360 and 2 pi. And then you can treat this just like a stoichiometry problem again, instead of doing your cross-multiplying with your proportions like we talked about before. So I can do 540 times 2 is 1080. I need to simplify that, and it gives me just 3 pi. Again, keep it in terms of pi to make your life a little bit easier. Once we get past that, we go into what's called angular velocity. So it is the speed, or how quickly you are changing your angle over time. So you can go through, a 2 pi rotation, but you can do it slowly or you can do it quite quickly. And those are going to have a different angular velocity based, again, on whether you take your time going in a circle or you go around very quickly. And that's what this is going to figure out. Your angular velocity is always this lovely Greek-looking W, which is just your omega symbol, and it's lowercase. So my omega is always equal to my theta, which was your angular displacement per time. Again, it's how quickly you're going through that rotation. Again, with your theta always being in radians. So again, it kind of narrows down that you have to use your dimensional analysis, so what we talked about a minute ago, to make sure that your omega is always radians per whatever unit of time I ask for. So, for example, here, 7.3 revolutions in 5 minutes. It does not specifically say which unit of time or unit of measurement I want it in, so I'll actually do this in a couple ways just to show you. So my omega, I'm going to start it out, it's theta, which is the 7.3 revolutions per time, so 5 minutes. But I need to convert this, and I specifically need to convert my revolutions into radians. So I'm going to do it just like before, where I'm making sure that my revolutions cancel. The nice thing that I like about doing it this way is that now I can see that my units are currently radians per minute. This problem doesn't give me a unit of time, so I can just use that. I'm going to multiply straight across. I always leave my pi out of it. So I'm going to do 14.6 pi over 5, and this would be radians per minute. I keep my angular velocity exact because you're going to use it again in a minute for our third step here, and so I will never round this number. Had I done this slightly different, and say I wanted this in radians, oopsies, per, say, second, we're going to have to do 2 rounds of dimensional analysis for this, and I'm going to show you really just how this problem would only slightly vary. We would start it exactly the same way. We would still convert my revolutions into my radians, but now we wouldn't be done because I have it in radians per minute right now, and I need this bottom row to say seconds. So I'm going to do another round of dimensional analysis, converting my minutes, which I'll put up top because again I need minutes to cancel with minutes, into seconds. But I need to know that actual dimensional analysis. 1 minute is 60 seconds. And then we'll do the same thing. So 14.6 pi over 5 times 60 is 300. And that would be the radians per second that it's going through. So it's a slight difference when I ask for a specific unit of time. Okay, so I want you to try this one. It specifically asks for radians per second, so give that a try, and then unpause the video when you're ready to hear my explanation. Your omega is still your theta per time, and your theta is 5.2 revolutions in 4 hours. But I need to convert a couple things. My revolutions needs to be in radians, and my hours needs to be in seconds. And you can do this in 1 jump or 2. So you can go from hours to minutes is what a lot of people like to do, and then go from minutes to seconds. Or you can do it at once if you know 3,600 seconds are in an hour. But then I'm going to multiply straight across, so this is 10.4 pi over 4 times the 3,600 is 1440. And again, I'm just going to leave that as is because I like to keep these exact. Okay, go ahead and try this one, and then I will talk it through. Doing your theta per time. We're going to start with 300 revolutions in 2 weeks. My revolutions needs to be in radians. And my time now needs to switch from weeks into minutes. And again, you can do this in little jumps or big jumps. In 1 week, there are 7 days. In 1 day, there are 24 hours. And in 1 hour, there are 60 minutes. So again, if I check my units and make sure they cross out correctly, that should work for me. So I have 600 pi over 2 times 7 times 24 times 60, which gives me 20,160. We can simplify this a little bit. If I divide them both by 20, should give me 30. Again, that'll simplify some more. 15 pi over 504, and that's probably about as far as it goes. On this section of the test, you will get a calculator, so don't worry too much about those large numbers. That's going to be fine. The most important one is really this linear velocity number, and this is what's going to come in most importantly. So it is the rate of change of how fast your object is moving in a line over time. And what you should be picturing, while I'm going in a circle, I'm still going this linear movement forward, as if you unrolled that circumference of the circle. You're figuring out that straight line that you're doing, okay? And you're always going to, your velocity, your linear velocity, is always your radius times your angular velocity. The angular velocity being what we just calculated, and then the radius being however large your circle was, whether we're talking about a tire or you're on a carousel or whatever it may be. What you're really doing, this is the primary reason that it needed to be in radians, because we're basically multiplying our circumference formula into this. Remember that radians are the base of it comes from finding circumference. You did 2 pi in there. We're going to multiply it by r, and it's going to find me the circumference in this formula. So we're going to go through this one together. Okay, an object is moving around a circle with a radius of 15 inches at 10 revolutions per second, and it wants to know the linear velocity. Again, here it hasn't really told me the exact units, so I get to assume that I can keep things as is. I do need to find, my omega first. That is my theta per time. My theta is the 10 revolutions, and it's in 1 second. I do need that to be in radians, again, because otherwise it won't calculate it correctly, but it doesn't talk about another unit of time, so I don't have to change it. So this is just 20 pi radians per second, and that's going to be my omega. My radius here is 15 inches, and again, it doesn't talk about that it wants it in a different unit besides inches. If this wanted to be in feet, we would have to do some conversion. This wants inches, so it's fine. So for my velocity, I'm just going to do the 20 pi radians per second times the 15 inches. And what it really does is cancels out that radians again and makes it calculate your circumference. And so it's going to be in inches when we're done. So when I type this in, I do 20 pi times 15. It's 942.5. If I round to the nearest tenth, this is going to be inches per second. So that's how many inches I'm going every second. And again, because this is radians, this basic multiplying by the radius really just calculates my circumference of that circle. Okay, so this, I've taken the exact same scenario to kind of drill down into what it means we have to do when I tell you the units I want it to be in. So we're going to do this one very similarly, but with some slight changes. Again, this one is going to start with my revolutions per second, which I will convert into 2 pi radians. But now I know I want it in miles per hour, so I have to convert the seconds into minutes and the minutes into hours. And again, you can do that in one big jump or in multiple. So I'm going to do 10 times 2 times 60 times 60, and this is 72,000 pi radians per hour. My radius is 15 inches, but I want it in miles, so I have to convert this. So we're going to do 2 rounds of stoich. Inches to miles, I'm first going to do inches into feet, so 12 inches are in 1 foot, and then 5,280 feet are in 1 mile. That is a conversion you will need to know what that's going to get me, and I'm just going to leave this as a fraction. So I just multiplied out the denominator. There, 15 inches are 15 out of 63,360 of a mile. So you have to convert both things, but now I can find my velocity by doing my omega times my r. So I'm going to do 15 divided by 63,360, and then times 72,000 pi, and I get 53.5 miles per hour. So again, this is the same problem we did a minute ago, but it required more transformation because I didn't want it in seconds, I wanted it in hours, and I didn't want it in inches, I wanted it, this should say miles. I apologize. Okay, I'm going to give you a minute to try this one. Really what I would suggest is pausing it and then listening to me explain it once you're ready. If you are not ready to try this on your own and you just want to hear me explain it, then that is fine as well. So linear velocity means I need to find my omega first. So I'm doing my theta per time. My theta is given to you here in this 300 RPM. 300 RPM tells you it is 300 revolutions per minute. That's what your car stat is giving you. Some people at this point in trig think it's radians, which is, I can see why, but just remember your car is telling you something that makes sense to everyone regardless of having trig or not. So your car is just talking about revolutions or rotations. So 300 revolutions per minute, is 1 revolution is 2 pi radians. And again, if you notice, I want it in miles per hour. So I need to convert my minutes into hours. And then I'm just going to do 300 times 2 times 60 is 36,000 pi. For my radius, I know the diameter is 32 inches, which means the radius is 16 inches. Again, I want it in miles. So it's going to be 12 inches is 1 foot, and then 5,280 feet is 1 mile. And so this is going to be 16 over that 63,360 number again. To get your velocity, we multiply those together. So I'm going to do 36,000 pi times 16 and divided by 63,360. And I get 28.6 miles per hour. I'm going to leave this one here as extra practice for you. If you want to try it, you can. I'm happy to help you out when I come back. But I do want to make sure that we talk about going the other way. Okay, here what we know the diameter of my bike tire, which really tells me my radius is 12. We know how far it goes total. And what I want you to notice about this problem, it's not talking about time. And so really my time doesn't entirely matter in any part of my equation. This 10 miles is how far you went total. And so it's my linear distance over here, like my linear velocity. And I want to know how many times it goes around, which is going to relate to this angular velocity number. Because again, my time is just not even mentioned here. And that is times the 12 inches. To solve this, I do need to make these numbers agree. So 10 miles and 12 inches, I can't keep them both like that. So you either need to convert miles into inches or inches into miles. I'm going to convert the inches into miles because we've already done that a couple times. It's 1 foot, and then 5,280 feet is 1 mile. You may notice those 12s just cancel out. So this is just 10 equals my omega times 1 over 5,280. When I solve that, my omega is 52,800. What's important to realize is this is in radians, and so I need to get it back into revolutions if I want to know how many times it goes around. So here is actually an example where we will divide by that 2 pi for it to cancel out. When you type this in your calculator, it's very important you put parentheses around that because otherwise your calculator will not do it correctly. But this answer I get is 8,403 revolutions that would take. There are also other ways to do this problem. I just wanted to show you a way that you could do it using your angular velocity, your linear velocity, and your angular displacement.